Hello and welcome to this video in two parts. The first part on the domain, range and roots of quadratic functions, and the second part on sketching quadratic functions. So we shall start with some definitions. The domain of a function is the set of possible inputs, and the range of a function is the set of possible outputs. And you will go into more detail on both of these in the Year 13 chapter on functions. The roots of a function are the values of x for which f of x is equal to 0. We are focusing on quadratic functions, and for quadratic functions all inputs are possible. There are no real numbers that you cannot substitute into a quadratic function, real numbers being the rationals and irrationals on our standard number line, not the imaginary or complex numbers. For this we write xer, as you can see, which is from set notation, and means x is an element of the real numbers. There are some functions that you cannot substitute numbers into. For example, 1 over x, you are not allowed to substitute the number 0 because that is undefined. And then there are other functions for which whole values, like all the negative numbers, may not be allowed to be substituted in. But in this example, you can always have any real value of x. However, quadratic functions will always have a minimum or a maximum point, and hence not all outputs are possible. From the graph we can see on the screen, the maximum point has a value for y of 4, and all outputs, all y values, must be less than or equal to 4, and hence we write the range as f of x is less than or equal to 4. The roots of a function, as was defined, are the values of x for which f of x is equal to 0, and hence represent the points where the curve either intersects or meets the x-axis. It is possible for a quadratic function not to have any roots if it doesn't intersect or meet the x-axis. In our example here, it meets the x-axis at -1 and 3, so they are our two roots. So we're going to look at a few more examples. The domain of all our quadratic functions will always be xer. In this example, y equals x squared minus 6x plus 5. It has a minimum point. It's a positive quadratic. The minimum value of y is -4, so f of x is greater or equal to -4, and it crosses the x-axis at 1 and 5, so those are the roots. This graph has a maximum point at y equals 9, so f of x is less than or equal to 9, and it crosses the x-axis at -2 and 4. Similarly, this graph has a maximum point when y equals 4, so f of x is less than or equal to 4, and it crosses the x-axis when x is -3 or 1. And of course, we could use completing the square if we needed to work out the turning point. The maximum or minimum point will always be an integer. In this particular case, I've completed the square, and we can see that when x is -5 over 2, the smallest value is -1/4. So f of x is greater or equal to -1/4, and the roots are -3 and -2. Similarly, for this graph, I've completed the square. The minimum value of y is -81 over 4, or -20.25. So again, the range is f of x is greater or equal to -20.25, and it crosses the x-axis at -3 and 6. For y equals 18 minus 2x squared, you could factorize out the 2, and then you'd have a difference of 2 squares with 9 minus x squared. So it intersects the x-axis at -3 and 3. And the maximum value lies on the y-axis. There's no x term to move it left or right. So the range is f of x is less than or equal to 18. This equation is already written as a completed square, x plus 2 all squared plus 3. So the minimum value of y is 3 when x is -2. So its range is greater than or equal to 3, and it doesn't have any roots because it doesn't intersect the x-axis. Similarly, this is a negative quadratic, so it has a maximum point at 8. It's already in the completed square form, so that occurs when x is 1. The range is f of x is less than or equal to 8, and it cuts the x-axis at -1 and 3. And of course, just to remind you, all these domains are xer because all inputs are possible. You won't always have the graph to get the information from, so let's imagine we're asked to find the range and roots of y equals x squared minus 6x plus 2. Well, the domain is xer, we won't ask for that, but that's always going to be the case for a quadratic function. If we complete the square, we get x minus 3 squared minus 7. So that's going to be -7 as a minimum point. So the range is f of x is greater or equal to -7. It's a positive quadratic, so it has a minimum point. And if we were to put y equal to 0, we could add 7, square root, and add the 3. And our two roots would be 3 plus or minus root 7. Now we're going to have a look at sketching quadratic functions, for which there are some main features that we will need to look out for. Again, the roots, The general shape, will it be a U-type shape or an N-type shape, a smiley face or an unhappy face? The coordinates of the turning point and where it crosses the y-axis. These are the points and the shape that you'll normally be looking for on a sketch. So we're going to start with level 1, quadratics which factorise without any repeated factors. So for y equals x squared plus 2x minus 15, it's a positive quadratic. If we complete the square, the turning point is at -1 at -16. It crosses the y-axis when x is 0 at -15. And if we factorise it, the roots are -5 and 3. Now I've used the graphic package Desmos to draw this, so you don't need all these numbers on the axes. Okay, but you can see that the graph cuts the x-axis at -5 and 3. The y-intercept is -15. You can see near enough that the turning point would be at -1, -16, and you can see the shape is a positive quadratic shape. It's the same for this one, except the coefficient of x is an odd number, which means that I get fractions from my turning point. The general shape is the same, positive quadratic. The turning point is at 9/2 minus 121/4, crosses the y-axis at -10, and the roots are -1 and 10. And this is the shape. Just remember to make sure that you actually label the significant features. What we have here is level 2, which I've called quadratics, which factorise with repeated factors. So x squared minus 6x plus 9. If you complete the square or factorise it, you just get x minus 3 squared. So the roots are 3 twice. It has a turning point, therefore, at 3, 0. And it meets rather than intersects the y-axis. Crosses the y-axis at 0, 9. And again, it's a positive quadratic. So here's its shape. And as you can clearly see, it touches the x-axis at 3, but it doesn't intersect. Our next level is negative quadratics. We can clearly see the negative x squared in the equation. So the general shape is upside down quadratic. If we complete the square using the method I showed you before with changing all the signs of the terms, putting the negative sign outside, we end up with y equals 64 minus x plus 5 squared. So the turning point is at -5 and 64. Clearly cuts the y-axis at 0,39. And if you factorise it, the roots are -13 and 3. And here's your graph. Again, make sure that you actually plot or state the coordinates of interest. Okay, level 4, this quadratic doesn't factorise. Not only does it not factorise, it doesn't actually meet the x-axis. So it's a positive quadratic. Its turning point is at 2, 2, which confirms it has no roots, and the y-intercept is at 6. And here's our graph confirming that it has no roots. And finally, just for fun, level 5, quadratics which do factorise but don't look like they will because one of the numbers is very large, and most of us don't know our times tables that high up. So it's a positive quadratic. If we complete the square, the turning point is at 3, -40,000. The y-intercept at -39,991. And if we put y equal to 0, we can solve for the roots. They are -197 and 203, which are 3 plus or minus 200s. And it looks like this. Clearly the numbers are so big that it's very difficult to actually see that the turning point is not actually on the y-axis. But then that's where your labeling your points would come in. Thank you very much for watching.